Hello everyone, and thank you for attending today's webinar titled Optimizing Yield for Lithium-Ion Battery Electrode Manufacturing for both Wet and Dry Processes. My name is Jeff Kenvin, and I'm the Vice President of Science at Micromeridics Instrument Corporation. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple engagement tools you may use. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A. We will try to answer these during the webcast, but if we run out of time, it will be answered later via email. Additional materials are available in the resource list. We encourage you to download any resources or links that you may find useful. Some networks cause slides to advance more slowly than others, so logging off your VPN is recommended. If your slides are behind, pushing F5 on your keyboard will refresh the page. If you experience any problems during the session, you can find answers to some common technical issues located in the Help Engagement tool at the bottom of your screen. An on-demand version of the webcast will be available after today's session and will be emailed to you once the session has concluded. Pleased to introduce our speaker for this webinar, Nicholas Monroe. Nicky joined Micromeridics in 2021 and is currently part of the application team here in Norcross, Georgia. Nicky graduated from the University of Delaware and from their very challenging BS/MS program for chemical engineering with a specialization in particle technology. During his master's thesis, he successfully applied DEM to study particle-particle and particle boundary interactions on powder bed structure and stress distributions. His background in chemical engineering and particle technology provide a great foundation for him in his current role as a powder rheologist here with Micromeridics. Nicky, it's an honor for me to introduce you today. We're so glad you could be here today to share your insights on optimizing yield for lithium-ion battery electrode manufacturing for both wet and dry processes.
Thank you, Jeff, for that introduction. Micromeridics has a full line of instrumentation that can help characterize different stages in the lithium-ion manufacturing process. Today we're going to be focusing on the powder flow and particle interactions, which can help be used for both wet and dry processes to improve yield in lithium-ion batteries. Today we're going to be discussing how to use the FT4 to help improve homogeneity of slurries and to help increase yield in electrode casting. We'll also discuss how to control batch-to-batch variation and use the data from the FT4 to establish quality standards. Due to the highly variable nature of powders, their flow properties can be dependent on a wide range of different properties fundamental to the powder, such as mechanical interlocking, size distributions, cohesive interactions, and more. Because of this, it's advantageous to run multiple tests and characterize the powder in a wide variety of environments. Thus, the FT4 comes equipped with 3 categories of tests, such as dynamic flow, bulk, and shear properties, each of which can shed light on the powder's flow behavior in a wide range of applications. Within the dynamic flow properties, one test, the stability and variable flow rate, can characterize the powder under a wide range of different parameters, such as specific energy, flow rate sensitivity, and its basic flowability. The main operating principle for the FT4 is for the blade to rotate at a defined helix angle, meaning that it is spinning at a defined rotational speed and moving axially at a defined speed. While it's making this helical traversal, the FT4 will measure and record 3 main parameters, being the torque, the force, and the height of the blade within the sample. The FT4 has 2 main operating modes in dynamic testing. This includes conditioning and testing the powder. During the conditioning cycles, the blade is rotating with the sharp edge facing forward so that we can get a gentle slicing motion through the powder sample. This is meant to help homogenize the sample and create a more even distributed packing structure. This can help reduce operator influence and improve repeatability of test data. When the blade's rotating in the opposite direction, we get a more aggressive compaction of flow, meaning that the the force and the torque values we make during this traversal are better used to characterize the powder's resistance to the blade's motion. The main FT4 methodologies that we'll be discussing today to characterize powder flow in battery applications are stability and variable flow rates and permeability. Micromeritics offers a wide range of instrumentation to help optimize lithium-ion battery manufacturing processes in both wet and dry manufacturing. Here we will be discussing how to define quality control standards for lithium iron phosphate in cathode manufacturing. Here we will be taking a look at the stability and variable flow rate test. For this test, we will implement the helical blade accessory, as well as either the 25 milliliter or 160 milliliter split vessel, depending on which vessel size you are using. During this test, we will complete one initial conditioning cycle before splitting the vessel open in order to isolate a known powder bed volume. After completing the initial conditioning cycle and splitting the vessel open, we will then subject the powder sample to repeated cycles of conditioning and testing the material to characterize how its flowability changes under repeated test cycles. Once this is complete, we will then complete the same process, only adjusting the tip speed of the blade during each test cycle to measure how sensitive the powder is to changing flow rates. One of the parameters that we can measure from this test is the specific energy. The specific energy represents the powder's resistance to the blade's upwards traversal and thus reflects the degree of interparticle friction and mechanical interlocking. In this example, we see that batch 1 yielded a much lower specific energy compared to the other samples, meaning that it has less significant interparticle friction. This corresponds with a more homogeneous slurry and higher yield in electrode production compared to batches 2 and 3. By using these results, we can establish quality control criteria for specific energy so we know whether or not the incoming materials will homogenize in a slurry and thus produce a high yield product. With this quality control criteria established, we now know that any incoming materials which yield a specific energy value below this criteria will produce high yield in electrode production and form homogeneous slurries. The next test that we will discuss on the FT4 is permeability testing. During permeability testing, we will feed air at a constant flow rate through the powder bed sample and vary the compacting force that we are applying to the powder sample. At each stage of compaction, the pressure drop that the air experiences as it transmits through the powder bed is going to be recorded. Highly permeable samples will yield a lower pressure drop as they are more able to transmit air through the powder bed, whereas low permeability samples correspond to a higher pressure drop value. This can help characterize the powder in terms of its air entrainment, packing efficiency, and response to applied stress. With our 3 batches of lithium iron phosphate, we can see that batch 1 yielded a high pressure drop value corresponding to a low permeable powder. This is due to this sample's increased solids packing efficiency, which prevents air transmission. This corresponds to more homogeneous slurry and better processing performance for batch 1 compared to batch 2 and 3. We can once again establish quality control criteria for pressure drop values during permeability testing, which allows us to predict whether incoming materials will form homogeneous slurries and produce high yield in battery production. Thank you for joining me today. If you'd like to learn more about how our instrumentation can help support lithium-ion battery manufacturing, please visit us at micromeritics.com. I'll now open it up to any questions.